Hello everyone. So in this video we're going to talk about section 8.1 which are talking about inverse trigonometry functions, and specifically we'll talk about inverse sine, cosine, and tangent, and we'll talk about the other three in section 8.2. So I know this is all new stuff, and so we're sort of turning a new direction after exam 2. Hopefully this won't be too bad of a turn. For this video, I'm going to use some completed slides. So I've written out all the solutions here just so I can have sort of better video quality. I'll talk through them slowly, and these are also on D2L. So you can sort of mold this video and looking at the completed slides. Hopefully that'll be a nice addition for you. So we'll start off with talking about the inverse sine function. And so this is going to have to bring back your sort of memories or your knowledge about inverse functions. And so I'll try to do that as much as possible when I can. So here's the first recall. So from section 6.2, a function is one-to-one. If it's one-to-one, then it will have an inverse function. Okay, so we talked about one-to-one before, and we also talked about inverse functions, and we're going to need to use the both. Okay, if a function isn't one-to-one, so we'd like to have a one-to-one function when we work with inverses, because if it is one-to-one, we know it has an inverse. If a function's not one-to-one, maybe what we can do is restrict the domain of that function, so really restrict where we look at it, so that the function is one-to-one, and then an inverse exists in that little section that we're looking at. Okay, and so here I ask a question that would be interactive if we were face-to-face, but of course it's not here. Is the sine function one-to-one? And the answer to that is a resounding no. Here's the sine function in black. Okay, the sine function is a periodic function, and so it actually repeats itself many, many times. And so the horizontal line test for a one-to-one function definitely does not pass. So the sine function itself is not one-to-one, and so it doesn't have an inverse if we look at the whole domain. But what this picture shows is if we restrict our view to some region, and the region that we'll actually pick is from negative pi over 2 to pi over 2. That's the blue part of the function there. If you look at that, it does in fact pass the vertical line test. So we went from the sort of bottom of the minimum. We took the minimum value at negative pi over 2, and then we went all the way up to the maximum value that we saw happens at pi over 2. And so it's always increasing during that segment there. And so it is a one-to-one function if we just look at it. The sine function is one-to-one if we look from negative pi over 2 to pi over 2. And so that's what we're going to look at. The sine function from negative pi over 2 to pi over 2. In that case, it does have an inverse. Okay, so how would we define an inverse? Well, we're going to do it the same way that we do any other inverses. If I ask you to find the inverse function of any function, what you should do is you should switch x and y and solve for y, right? And so that's what that first line says, that the inverse sine function, so y equals inverse sine of x, means x equals sine of y. Okay, those two statements are equivalent. Basically what they're doing is switching the x and y. Okay, not the x and y of like the left thing turns into the right. Hopefully you know what I mean. Okay, so the inverse sine function, like any inverse function, so when we talked about inverse functions, we've talked about how to find them, and then we've also talked about their domain and their range. And so what we found is that the domain and the range of the inverse function are sort of the flips of the original function. So the domain of the original function becomes the range of the inverse function, and the range of the regular function becomes the domain of the inverse function. Okay, and so that's the same thing that happens here. The range of the original function of sine of x was from -1 to 1. Okay, and so that becomes the domain of the new one. Okay, so -1 to 1, and then the range of the inverse function becomes the domain. Sorry, the domain of the regular function becomes the range of the inverse function. And so since we restricted ourselves from to the region -pi/2 to pi/2, that becomes our range. And so that inverse sine function is only defined from -pi/2 to pi/2. Great. And so there's a picture. Sine, the original function, is in red, and the inverse function is in blue. All right. And so we're going to be finding the inverse, the exact value of an inverse sine function. So we're going to try to evaluate this. And if we were in person, this slide gives you values of sine throughout, which will in fact be helpful. Okay, will be helpful. But for this sort of case that we're working with right now with these videos, it's not going to be as helpful. All right, so here's the first section where I actually try to do some work. So these are problems that you could see and you will see on exams, homeworks, quizzes, all kinds of stuff. So forgive me that all the work is there. I'll walk through it step by step. So we're trying to find the exact value of the inverse sine of -1/2. Okay, so if you'll notice, if you have your calculators out, which you should get them out because the next slide is talking about using calculators to find these values, you'll see that the inverse sine is a button, or it's really above sine, but it's on your calculator. And so you could say, oh, well, this is an easy problem, and that's true. You can substitute or plug this into your calculator and get a number out. But when I ask you to find the exact value of the function, that means without a calculator. So, first one, inverse sine of -1/2. Now, we don't know how to work with the inverse sine function. It's hard to work with. Okay, and so what we want to do is we want to use information that we do know stuff about to solve this. And so this is going to be a general strategy that we use throughout Chapter 8 that you're going to have to get used to. We take the expression that we want to find the exact value to, and we set it equal to some variable. The variable I'm going to use is theta. Okay, so if you look on the far left, I don't know if you can see my cursor, but if you look here on the far left, I've set the original equation, or the original expression here, equal to theta. Okay, so that may look, it may be weird to you why I did that, or it may look harmless, but it's actually going to help us solve this problem. And so by doing that, I've sort of reformulated the question I'm asking. The question I'm asking is to find that value of theta. Okay, find what theta equals. So the next step that I can take, and it's also important to remember that theta has to be between -pi/2 and pi/2, because that's where sine inverse, the range of sine inverse is. Okay, so it's defined from -pi/2 to pi/2. All right. The next step is I take the sine of both sides. Okay, and when I take the sine of both sides, the sine and sine inverse cancel out, and I'm left with sine of theta equals -1/2. Okay, so that's also an operation that we're going to be doing a lot. So you have to get used to that, or hopefully it's not totally foreign to you. And now I have a totally new question, or totally new thing that I'm trying to solve. the sine of theta equals negative a half, which is much easier than the sine inverse of negative 1/2, okay? Because we know how to work with sine, cosine, tangent, those type of functions a lot better than we know how to work with sine inverse. So we've translated this problem into an easier problem. So now I'm going to ask, what's the value of theta? Which really, what I mean is what the sine of what angle is equal to negative a half. So these examples are going to be filled with numbers that come up a bunch that are from our special right triangles. And so usually when I see a 1 and a 2, I'm going to think, there's a special triangle that has sides 1 and square root of 3 and hypotenuse 2. So, and it turns out that's called the 30, 60, 90 triangle. So that's what I'm going to use. All right. So great. I think I'm going to use that triangle. And so this is where we'll start to go over to this picture. Okay. So I'm going to use that triangle. And now I have to think about where that angle lies in the XY plane, which we've been working with a bunch. Okay. And this is where the range of theta comes in. So way back in the first part of this problem, when I said, when I equated theta and sine inverse of negative 1/2, I said that theta has to be between negative pi over 2 and pi over 2. That translates to theta being in either the first or the fourth quadrant. Okay. So the first quadrant is from 0 to pi over 2 counterclockwise, and 0 to negative pi over 2 if I went clockwise. That's the fourth. First is 0 to positive pi over 2. So it's either in the first or the fourth quadrant. Then I need to string together another fact that I know, which is where sine is positive. So we know that, or we've talked about, hopefully a little bit before, that the sine of an angle is positive in the first and in the second quadrant, and it's negative in the third and the fourth. So with that fact in mind, I know it has to be in either the first or the fourth, and I know that sine is positive in the first. So it can't be in the first quadrant, it has to be in the fourth quadrant. Okay, so hopefully that explanation made sense. I know it was a little bit of a long one, but hopefully that made sense, that I've narrowed it down based on the fact of theta having to be between negative pi over 2 and pi over 2. That narrowed it down to the first or the fourth quadrant. And then the fact that down here I said that sine is negative because the sine of whatever angle that I'm going to choose is equal to negative a half. That means it has to be in the fourth quadrant. So that's in fact where I draw my 30, 60, 90 triangle. Okay, so I drew a triangle, and then from this fact that the sine of theta is equal to negative a half and sine is opposite over hypotenuse, that means that this has to be negative 1, okay, and the hypotenuse is always positive, so it's positive 2. And then I can complete that third side. It's not really helpful for me, but I can complete it. It's positive square root of 3, because you can think of this as in the XY plane, okay, and that angle, or the terminal side of that triangle, really the angle that we're looking at, it's in the fourth quadrant, which if I put a point on it, the point would have a positive x value and a negative y value. All right, so I've reasoned all the way down through to here, and then I have to think what angle is opposite the side of the 1 in a 30, 60, 90 triangle. And in fact, it is the 30-degree angle. And from now on, we're always going to think about these in radians and not degrees. And so 30 degrees is pi over 6. Okay? And then, of course, it has to be negative because it's in the fourth quadrant. So finally, I get all the way down to the answer of negative pi over 6. Okay? So I know that the sine of negative pi over 6 is negative a half, which means that this expression that we were trying to find originally is negative pi over 6. Okay, so that was a very long explanation of a problem that's not that complicated, but I wanted to take time to try to give you that information. All right, so now I'm going to go through this next one much quicker. So I want you to find this exact value of sine inverse of 1. So I do the same thing. I set it equal to theta, and then I move the sine over. And so I get sine of theta is equal to 1. That does not trigger, for me at least, any special triangles, either 30, 60, 90 or 45, 45, 90. And so I've got to think sort of outside the box about 1. And it turns out that if you draw the sine function, so I have to think, where is sine of theta equal to 1 when theta is between negative pi over 2 and pi over 2? So I drew that function over here on the right, and it turns out that the only place that happens is at pi over 2. So it turns out that the answer is pi over 2. Okay, so I didn't take nearly as much time on that one because I tried really hard to explain all of it on the first one. Now, finding the approximate value of the inverse sine function, meaning finding it with a calculator. Now, I can't, of course, show you a calculator in this video, okay, but I have a TI-83 calculator in my hand, and I'll try to, in the best of my ability, describe very quickly what to do. So the sine inverse button, if you're on the TI-83, 84 type calculators, will mostly be right above the sine button. And so you have to do second sine, and that will give you sine inverse, and then you just substitute in the number. Okay, click enter, and then it should give you out a number. Now be mindful of what mode your calculator is in. Okay, from now on you might as well just keep it in radians. Okay, unless I ask you something specifically in degrees. So both of these were radians, not degrees. And so the values are negative 0.5236 for sine inverse of negative a half and negative 0.2527 for sine inverse of negative quarter. Okay, so that's it for the calculator type stuff. It's really simple. Okay, you'll be tempted to just do that for every question, but unfortunately it doesn't quite work that way. All right, and by the way, we did sine inverse the exact value in this first equation, and you'll notice that it's negative pi over 6. If you do negative pi divided by 6, the decimal is going to be negative 0.5236. Okay, so side note. Now, properties of the inverse sine function. So these will be also important. What can we do with these inverses? And so part of what we did sort of behind the scenes in the first slide, okay, not the approximate value, but in that first slide, is that we took the sine of both sides, and that somehow canceled out that sine inverse, and we were just left with a value. So if we go back here and we see the second step in both sides, we somehow got from theta equals sine inverse of negative a half to sine of theta equals negative a half. And so I think you've probably seen this somewhere in the long distant memory of yours. So we have these properties. And so they're up there in the yellow box, that sine and sine inverse cancel each other out if the thing inside, the x, is between negative pi over 2 and pi over 2. Okay, and that has to do with the range of the function, the range of sine inverse. Okay, so if it works out that way for sine inverse of sine, great. If it doesn't, we've got to turn to something different. We've got to do more work. And so you'll see down below that the first one is an easy question. Turns out really nice. The second one, not so nice. All right. And then similarly, sine of sine inverse also cancels out when the thing inside sine inverse is between -1 and 1. Okay, so if you'll look back to that first page that we did, and we sort of assumed that second line there, but it turns out that it was an okay thing to assume because both values were between -1 and 1. All right, so first example, find the exact value of sine inverse of sine of pi over 8. Pi over 8. And that is an easy answer. It's pi over 8 because pi over 8 lies in between -pi over 2 and pi over 2. Okay? So, and hopefully that's clear that it lies in between the two. So, great. Hopefully all the questions will be like that for you. Unfortunately, they won't. Okay? You can always hope, but there will be some not so nice ones. So that's the nice one. That's the one we always hope for. The second one, sine inverse of sine of 5 pi over 8. Okay, so now we have 5 pi over 8, and pi over 2 is equal to 4 pi over 8. And so 5 pi over 8 is bigger than pi over 2. And so it does not lie in that region. And so we've got to do some extra work to get there. The way that we solve this problem is going to be just like the way we solved the other problems at the beginning. Okay, so you'll see that first step that I do, I set everything equal to theta, and so you'll hopefully find that I do that because I'm trying to get rid of the sine inverse. Okay, I'm trying to get rid of that sine inverse function because I don't like inverses. So if I can do that by setting it equal to theta and then doing some manipulation, I'm going to do that every single time. So that's what I do. First step, I set that whole big thing equal to theta. Then I take the sine of both sides. I know that the sine of any value, 5 pi over 8 or whatever, is going to be between -1 and 1. And so that thing inside is okay. Like the properties above in that yellow box work out. So to get from the first to second step, I'm okay because of that first, really because of the second property in the yellow box. So now I get that the sine of theta is equal to the sine of 5 pi over 8. So I need to find a value of theta that lies in the first or the fourth quadrant. Okay, because that's how I define theta up here. It has to be in the first or the fourth quadrant by definition. So I need to find an angle there that has the same value as 5 pi over 8. And the strategy that I'm going to use is called the complementary angle approach. Yes, complementary angle. So, no. I forget what it's called, but I'm going to go move forward. So when you have 5 pi over 8, and so I've drawn that over on the right, okay, in the picture. And so really, when you do that, when you try to draw the picture and find sine of 5 pi over 8, you then use, for the life of me, I can't remember the theorem, and that's bad because I'm making this video. I should remember, but I don't. 5 pi over 8, I find the angle that takes me to get to pi, okay? And so it turns out that that's 3 pi over 8. And by the theorem that I can't remember for the life of me, it says that the sine of that angle and the original angle that I'm going to use, okay, so 3 pi over 8 and 5 pi over 8, they are the same up to the value of the sine, okay, up to the value of the sine. So the sine of 3 pi over 8 and the sine of 5 pi over 8 can be very similar they're going to have the same number, but they may have differing signs. So 3 pi over 8 is an option. And so to make sure that it's actually the option that we want, we need to think about where sign is positive. Sign is positive in the first and the second quadrant. So I know that the sign of 5 pi over 8 is positive, and so and also that the sign of 3 pi over 8 is positive. Okay, and so that together gets me that the sign of 3 pi over 8 divided by sine 3 pi over 8 is equal to the sine of 5 pi over 8. And so 3 pi over 8 is my final answer. Now, that was, again, a long example, and it took a lot of twists and turns, including me forgetting the theorems that are important in this class. But hopefully that made some sense. I know my jabbering doesn't make a lot of sense, but hopefully the info actually on the screen makes sense. All right, so that's where we're going to stop, and we're going to move on to the inverse cosine function in the next video. It'll be much shorter than this one, and hopefully I'll remember the theorems that I need to. Okay, I'll see you next time.